Hi, welcome to Precalculus. Today's topic is graphing a polar equation, the case of a rose. So we have gone through several examples so far. We talked about lines and then circles and then limaçons. Circles were, for example, r is equal to 3 cosine theta. Limaçon, an example would be like 5 plus 7 cosine of theta. Now we are going to go one level higher up. We are looking at cases where it's not just a theta in our equation, rather it's going to be a multiple of theta. So a case of 1 theta is here, of course. We are going to look at 2 thetas or 3 thetas and so on. Just as before, we are going to have several cases so that our quick drawing can be helped with them, so we can make a table of what the pictures look like. So this is something you see in your textbook or in your software. We are going to divide the cases based on if n is even or odd. By odd we mean 3, 5, 7, etc., and by even we mean 2, 4, 6, etc. So case of 1 is not considered here because that was a circle, and 0 is also not considered here. Now, to be clear, to avoid a certain confusion, I have added a case down here. For the n's, we are going to have 2 categories, if n is 5, 9, 13, and so on. And if case of n is 3, 7, 11, and so on. I'm going to explain that as we go on. So 5 pictures. So as you see, the picture is quite symmetric. So this is called the rose, even though perhaps it doesn't look like a rose. It's called the rose, and it has some petals and it has a radius. It has some tips, and then it has angles at which the edge of a petal approaches the origin. These are things that we can we can use them to help us quickly identify a picture. Of course, to understand it, we have to draw it carefully by hand on a graph paper and get some practice with it. So each rose has a radius. This number that you see here, multiple, that indicates how big the radius of the rose is. So in this case, r is equal to 2 sine of theta. The tip of these petals goes as far as the distance of 2 from the origin. So that is a simple indicator for us what is the radius of the rose. Next question is, well, how many petals is it going to have? Well, we have 2 situations. If n is odd, for example 3, then the number of petals is exactly that number. So 3 theta, 5 theta, 7 theta, we are going to see 3 or 5, 7 or 7 petals for the rose. If, however, if n is even, the number of petals doubles up. We are going to see the number of the number of petals we are going to see. For example, this is a case of n equal to 2. When n is equal to 2, we see 4 petals. This is case of n is equal to 4. For n equal to 4, we see 8 petals here. So that is how many petals we are going to have. Next question is, well, where are these tips? Well, one general criterion is that they always form a regular polygon. Like if I connect this tip to that tip to that tip, I get an equilateral triangle. In this case, if I connect the tips to each other, they make a regular pentagon. This one is going to be a square, and this one, the shape with 8 sides, is going to be like an octagon. So the shape is very symmetric, very regular, and so that's going to be another item that helps us figure out what the true graph is. A bit more detail is, well, exactly where are these tips? So you see in this case, the tip is right on the x-axis, or the so-called polar axis, it at the location A. It so happens, for example, for all the in odd cases, A being positive, by the way, we always start from here. So this is always our starting location, and then we go around. For n being odd and using sign, starting point to orient ourselves is either this spot up here. There, that spot is always up there for the cases of n, 5, 9, 13, and so on. For the case of n being 3, 7, 11, we have another fixed spot, which is this point. That point is always on all of those pictures. How about the rest of the points? Well, the rest of the points, we have to do a little bit of calculation to figure out where these things are. So this, we say the whole circle is 2 pi. So take 2 pi and divide it to the 3 angles. So there's going to be 2 pi third and 4 pi third and so on. For the case of n being even, we have a different situation. For cosine, we always have these 4 spots always on our picture, and if you have more petals, well, of course we are going to have more of these points showing up, but they are going to be depending on where our n is. For the case of sine and n being even, perhaps the easiest way to think about this thing is like thinking about a pizza. That makes us hungry, but we here imagine you are having a pizza and you want to slice it up. So we always have possibility of slicing this thing on x and y axis, and then depending on how many petals you have, you're going to have more slices here. So here are my pizza divided to 8 slices. So this is for the case of n being of course n is even, and we are dealing with the sign. So we draw all these slices, and then the petals are fit inside of those slices. So this was a kind of a general remarks about how this roses look like. Now let's go ahead and draw them slowly to get a sense as to what happens as angle theta changes. How does our curve get to be traced out? So we are going to trace the curve. You might be wondering, oh, well, general question students ask, oh, what's the use of these things? They do show up in advanced engineering or physics classes, so the applications are rather advanced, so we cannot bring up the issue right now, but they do show up. For example, when you look at the topic of so-called Fourier series, sine and cosine of a multiple of an angle is a standard recipe there. Well, where do they use Fourier series? In signal analysis, signal transfer, and so on. Okay, now let me go and change the screen to draw these things slowly and get a sense of how stuff looks like. Okay, I made this little page here to explain this graph to you. So suppose I want to explain to you how do we trace 2 sine of 3 theta. We said several factors are present here. One is the radius of the rows. The other one, are we using sine or cosine function? And the third factor is, well, is it what kind of number do we have here? Is it even or odd? In some cases we had a split there as well. Easiest thing to look at is, what does R do? Well, here's making the radius bigger. It's simply radius, so there isn't that much mystery there, or simply changes the size of the picture. We said that there is an issue of what multiple do we have. Uh, the multiple of 1 we excluded because it's not a rows anymore. I mean, it's just a circle. So we just excluded that. 3, 5, 7, and 9, and so on. So the rows get more complicated, but let's go back to 3, which is not as trivial as a circle, and still shows the attributes of the rows. Now I go ahead and start drawing this thing. Let's see how. So this is my angle. C is the range for the angle. So I start at 0, and see, if you see, I am starting at in this case I'm starting at the origin, and this thing is building itself up, and it's going to come and make a petal, and then we see how does it, so it's going to go up here, turn around. So we started going at the angle of 0. Now we are coming down at a certain angle. What angle is it at which we are approaching the origin? This is going to be a question that is of interest to you first in calculus when you're going to do a certain problem there, just as a matter of practice, but later on for other applications in engineering. Our angle of approach is pi third. As I come back to the origin at pi third, I go hit the so what happens at pi third? Well, remember, this is a sine of 3 theta. So if your theta is pi third, 3 times that becomes pi, and sine of pi is 0. So as the argument inside the whole parentheses approaches to pi, we are going to approach 0, and that's when we are back at the pole. And then we continue. Well, where do we go next? Here is a general idea. The picture always it turns. It doesn't make a sharp corner or something. Just to see how it goes. It nicely, as if it's tracing a kind of like a circle at this point, nicely goes down. Where does it go? Well, of course, it's going to go down. It's going to go toward this point. Well, when does that happen? Our theta at that point has become pi over 2. When you multiply by 3, it becomes 3 pi over 2. Sine of 3 pi over 2 is minus 1. So r becomes minus 1, and that's why it brings us to this point down here. Let's continue. So I go here, and now I have hit that second tip of the rows, and then I continue. What do you think is going to happen next? Well, so my theta is increasing. The theta by now is here. We're getting around to 2 pi third. When I take that theta and triple it, I get 2 pi, and sine of 2 pi is again is 0. So as my angle approaches 2 pi third, my r, while being negative, is going to come towards 0. That's how it comes to 0. And then we continue. What do you think is going to go next? So we have the critical point pi third that brought us to 0. And then 2 pi third brought us to 0. The third approach towards 0 will be at a pi. So let's see. So we are going to go, we reach the tip, and then turn around, and by the time we hit pi, we get to the origin again. Now if we were to continue again for the next pi, we're just gonna repeat this picture again. So if from 0 to 2 pi, if you go from 0 to 2 pi, you're going to go through this rows twice, just like how it happened with the circles. We were traveling it twice if you wanted to go for angle of 2 pi. Same thing here. Okay, so how about other examples? Just do a bit of other cases as well. Let me go back up to uh, angle 0 and then go ahead and so we did sine. How about cosine? So let me go ahead and erase these things out and choose my cosine and also label it. Now we have cosine 3 theta. Let's go back and start again. So where does this go? Uh, Now you see the starting point. Starting point now is at the tip, the right tip. I just changed the angle. One petal finishes. You notice that we continuously go to the other side. We don't we don't zigzag between the petals. The picture just very nicely, smoothly, continuously goes, and then makes petal number 2, uh, petal number 3, second half of the bottom half of first petal, then it's created. So let me see. I erase it and do it again so that you see. Now we come to the origin. Next one. Next one. Back to the first. Now, if I had 5 petals, see, 5 petals. You see how does that go? Start from the origin. Again, we come here. We go to the quadrant number 3. Turn around. Quadrant back to 1. Quadrant 4. Finish with that one. Quadrant 2. And back to that one. So the way we travel through the edges is rather interesting by itself. Same picture repeats. If you have 7 of these, just quickly go through that one. So you remember we explained that there is that game spirograph that actually lets you draw these things by hand on a piece of paper, and even more complicated type of pictures. We are aided by the fact that this is a nice number. So if it was like square root of 2 or something, the picture, well, I let you go and discover what the picture looks like. It's going to be more crowded than what we have here. Okay, so we did the cosine for a variety of cases. Let's go back to the sine for the variety of cases. So we had sine of, we are still looking at the odd cases. So let's go back to 3. This is 3. Notice for the case of 3, starting point, best starting point I can tell you is down here. You start from down here and then make your regular shape. Now how about 5? Where does 5 go? 5, the starting point is this point up here. That's the good fixed point. All of these cases start from here. What do you think is going to happen to 7? 7 again starts from down here, like here. It starts from down here, and of course, where does 9 go? 9 starts from that location. So the idea I'm trying to refer to is if you want to have a fixed point to make sure you're making right choice on your rows, it's a good idea to have a fixed point so that your choice is clear, or that your orientation is chosen clearly. So let's go for example. So we did 3. Let's do 5 again, just to see how it is built. We are starting at 0. So in this software starts at 0. I set it to start at 0. So we go through these. Now, exactly where are these tips? We are going to talk about that by solving some simple equations. Uh, Solving equation comes up a little bit later than right now. However, we can, in this simple case, we can do that as a matter of practice. Okay, so what if I go to 7? We said 7 we expect to have a fixed point that is here. So we are going to have a regular heptagon. Heptagon means that's 7 sides. And let's see. So petal number 1, number 2, number 3. You notice we passed through this point. So if you want to make a choice, quick solution. After we've reached pi, we are going to repeat the picture. If we continue after that, for example, if you go from pi to 2 pi, the picture just repeats itself. Okay, so we did several examples of these. Now let's go ahead and take a look at cosine. So I forgot to erase the legend of my picture. Where was the legend? Sorry. Erase that too. Okay, let's go and choose case of even multiple. So here my multiple is called m, so that it doesn't mix up with the other group. So m theta, we are going to look at sine and cosine of m theta. Let's go look at cosine. Easier. So my range of angles now is called d. I'm going to change that. Let's see. What was our, let's just choose m to be a small number, 2. So what are we looking at? We are going to look at case of 2 cosine of 2 theta. So let's see. So in these cases, rather easy. These 4 corners are always in our picture, meaning what? Well, like if I go from 2 to 4, here I have 2 cosine of 4 theta. I'll go to 6. Intermediate points, they crowd up, but these 4 points are always there. That makes it easy and nice for us to deal with cosine of a even multiple of theta. It's rather easy. So facts here, the number of petals is twice as many as the number that you have here. So let's just make sure we understood that. So here I have 4 theta, I have 8 petals, and so on. So let's take this picture out and let me reset. So I reset. Now let's go look at the case of sine of even multiple of theta. In this case, we said an easy way to think about this is to take a pizza, slice it up to 2m slices. So there will be going to be m half slices per quadrant, and then draw our petals inside those slice marks. So let's take an example here. So I have, for example, sine of 4 theta. Let's see. So I expect to have 8 petals. So how do I get the picture right? I get Easy way to think about this thing is to take your pizza and divide it to 8 slices. How would you do that? Well, there's always X and Y axis, always a slice on those lines. And then, well, to make 8 slices, we need 2 more cuts in these directions. And then we have our 8 slices. Then inside each slice, we go and draw our rose or rose petal. Okay, so let's go in the easier case. For example, 2, the multiple is 2, so there will be 4 slices. So that is just your X and Y axis is going to do. We don't need any more. So the X and Y axis creates 4 slices. We are going to have big share of the pizza, and then we are going to have one big petal here in each of these. If we had m equal to 4, that's how it's going to look like. We just talked about that. 6, a lot more crowded. I'm going to be careful with that pizza now. You take this thing, you cut it on X and Y axis. Then, of course, you go ahead and divide each of these into 3 components. So at 30 degrees and 60 degrees, you make your cuts. And same way on the other side. And then you're going to put these narrow petals there, and etc. So here are it's going to be m is 8, and there will be 16 petals, and then here's going to be 20 of them. So so as to where the tips are going to be, well, that is going to require solving a trig equation, which is coming up. But let's see. Let's go back to our writing page and okay. So we got a sense on how do these curves come about? That is, when we are going to trace them, when r is changing as a function of theta, how does the whole rows show up? Now let's suppose we try to do some of this thing by hand or by the software that's available on LX for polar plotting. See how does that go? So let's start with not so crowded case. Let's say 2 cosine of 3 theta. That's the picture we expect there. Now, so suppose we are going to do hand drawing of r is equal to let's see, hand drawing of 2 cosine of 3 theta. So we are trying to reproduce this one by hand. We said an easy aspect of these problems is that, well, the radius of the picture is a 2. Whole thing fits inside of a circle of radius 2. So that is the first thing we pay attention to. So if it was 2 here on polar pages or polar software, they always draw the circle for you already, so you know from that circle that your picture is going to fit inside the circle. Okay, and then what? Well, then we make a table, and this depends on how patient you are with making your table. So theta, I want to make 3 theta first, and then I want to figure out what is cosine of this, and then so step by step I find out what is twice this cosine of 3 theta. Once you become familiar with this, you might bypass the intermediate columns and directly jump from one to the other one. So easiest starting point is 0. Triple of that is 0. Cosine of 0, we need to remember this from memory. so that we don't rely on a table or something that's going to make the process too slow. Double of that is of course 2. Now point with angle 0 and radius 2, well, that is this point. So that is one point that we have. The question is, what next angle should I consider? We are used to jumping from 0 to pi over 3 because those are the famous angles. But remember, we are tripling our angle here. So it's fine to have pi over 3 or pi over 6. I don't know what I just say. Pi over 6 would have been perhaps okay to jump all the way there, but we can go on smaller angle in order not to miss our petals. Otherwise, we might jump from one side to the other side without noticing what happened. So what do? Next, whatever famous angle I have, whatever comfortable angles I have, I take them and divide them by this number. So that's going to be pi over 18. Why? Because when I triple that, I get that famous angle pi 6. And I know cosine of pi 6 is radical 3 over 2. So if I do doubling of this, of course I get radical 3. So I know at the angle of pi over 18, which is about 10 degrees over here, I am at the location radical 3. So this was 2. So on this small angle, I am at some location, perhaps around here. Now I needed a graph paper, but let's just do this thing. So what is our next famous angle? Of course, after pi 6, I have pi 4. Pi 4, a third of that is going to be pi 12. When you triple that, of course, you get back your pi 4. Cosine of that is radical 2 over 2. You double that, becomes radical 2. So at pi over 12, which is about 15 degrees, so somewhere around here, I'm going to have at smaller radius. Well, what comes after pi over 4? After pi over 4, we have pi over 6, pi over 3. So I have pi over 9. Let's see. I need to redraw so perhaps the better way of doing this thing, here are famous angles 0, pi 6, pi 4th, pi 3rd, pi half, 2 pi 3rd, 3 pi 4th, 5 pi 6, and oh sorry, strange, and pi. I take these numbers and divide them by 3. So let me write here so I don't run out of room. 0, pi 18, pi 12, pi 9, pi 6. You notice that 2 pi 9, 3 pi 12, that is of course same as pi over 4. So this is our famous angle pi over 4. This is another famous angle pi 6. And then 5 pi 6, I'll have 5 pi 18, and then finally pi 3rd. So I took all of my famous angles, divided them by 3. to see what kind of angles to pick up. Now, you don't have to pick up all of these things, just enough of them so that you get a sense as to where the petals are and how to orient yourself. You get a sense of how this thing is developing. Of course, the higher the number here, the more angles you will have here to look at, and the job becomes rather daunting. But it's doable. Pi over 9, so I look at the next number in the list. I triple that, it's pi over 3. Cosine of that is 1/2. Double of that is just 1. So what does that mean? It means at an angle of 20 degrees, we have reached half the radius. And then we continue going. So that was pi 9. Then I have my pi 6. Triple of that is what? Triple of that is pi over 2. What's cosine of pi over 2? That's a critical point. It's a 0. Double of that, still 0. So what is this? This is the important point. What is this? This is when we have, so at pi 6, we have made it back to the origin. So this petal, or half of it, started forming here at angle of pi 6. This is sometimes referred to as angle of approach. And that is something you are going to need in your calculus, because you need to know when does this thing come back. So it comes back at pi 6. We had two important milestones. One was this one, which is the tip of the petal, and the other one is where that petal ends and the next one starts. Now I let you continue, or maybe I just make one more of these things. So for example, what's the next point? 2 pi 9. So what's that? 2 pi 9 is 40 degrees. I'm somewhere here. So where's my curve? Now triple of that is 2 pi third. 2 pi third, I make a cosine of it. Cosine of 2 pi third. Important thing is that now it has become negative. Is that right? Cosine of 2 pi third is negative 1/2. You double it, you get -1. What does that mean? At 2 pi 9, which is somewhere around here, like almost 40 degrees, where is my rose? The rose continued on the other side. You have to go on the other side. So the angle by now is 2 pi 9. That is where the axis is. Where is -1 on that axis? It's on the other side. Okay, so what happens? What happens is that the petal continues on the so we continue listing points. It's going to be a bit easier on the plotter, but just to get on the idea. So we have next 3 pi 12, triple it pi fourth. Cosine of that is radical 2. Excuse me, 3 pi fourth. Cosine of that is minus radical 2 over 2, and double of that would be minus radical 2. So at pi fourth, we are going to be at minus, so at pi fourth we are going to be at minus radical 2. We continue going. Let's pick some other points quickly. 5 pi 18. We triple that, becomes 5 pi 6. Cosine of that will be minus radical 3 over 2. Double that will be minus radical 3. So that is where we are going to be at. And let's go to a nice point, pi third. Triple of that is pi. Cosine of that is -1. And we have reached the tip, -2. So let's go back up here. Where was he? So at pi third, by the time our angle comes to pi third, we have gone to the other side. We are at -2. So the picture has reached this tip. And if we continue, we'll have 3 more of these things. Let me just draw them in perhaps different colors. We are going to have next, and then the next one. Let's draw it some other color. By the time we come back, we have the rows. Okay, so this is by point plotting, seeing how the trace is developed. Now let's go ahead and do the same thing on Alex. See what does it look like over there. Let me go make the page. Okay, here we are on Alex page, asking us to graph r is equal to 4 cosine of 3 theta. So the only difference between this and what we were doing a moment ago is that the radius is 4. Radius is 4, so it means, well, that's good because we don't want a very small picture either. So the bigger that r is, the easier it is to see. So what are the ways of doing this thing? So it's a rows. We know it's a rows because a multiple of theta is a number bigger than 1. Well, for odd multiple, it's just that many petals, so it's going to be this one. Yeah, and then it's asking where is the first petal. Well, yeah, here we are going to control it, and here's the first petal of this thing. So we here's my first petal. Where is the second petal? Well, at 2 pi third. Oh, wrong radius. Let me erase this thing and start over. Let's see. So we were on arrows. Select. Let's see if I can have a steady hand. And then radius 4. That was my mistake. Okay, here's radius 4. And then how about the third one? Okay, let's not lose the radius again. It has to make a equilateral triangle, so it has to be at the angle 0, 2 pi third, and 4 pi third. So here is the next one. So what we did was by just adjusting, we didn't do point plotting. Point plotting would have required us to do this one, and would have taken much longer. So that is how we approach this problem. Let's see if we are right or what. Well, thankfully we are correct. Now can we do this thing again? Because I wanted to do it by point plotting. Let's see. Well, the problem is considered finished, so let's see if we can start another problem. Okay, here is log of the draw. Now we have r is equal to 4 cosine of 2 theta, and now we are taking an example of a multiple being an even number. So you remember in that case we had twice as many petals, and easiest thing was to consider x and y axis as signpost for us, and get our bearing according to that. So instead of going through what we did last time, which would be perfectly okay, let's do point plotting, see how does this go. So we expect this to take quite a bit longer because it's just laborious to get all the points there, but that's the only way we see how this thing is shaping up. So that is, let's see. So it says don't approximate, give exact values, and so on. So let's start at angle of 0. Cosine of 0 of course 1. We are at distance of 4. So that was good. Next question is, what next angle should we consider, or is the software smart enough to go half of that angle? Why should I consider half? Because I'm doubling it here. I'm doubling it here, and so the double of that will be pi over 6. Let's see if it works. If not, then we are just forced to pick all these angles. I haven't tried it before. Let's see. So I have pi. My angle there is pi 6. I take that divided by 2. So pi over 12. Let's see, is happy with that. So pi over 12. Why? Because when you double it, you get pi 6. Cosine of pi 6 is going to be radical 3 over 2 times that becomes 2 radical, so 2 radical 3. So we see it's a reasonable place. Let's continue. What's next? Pi 4. So it does work. So pi 4, I can here is my angle pi over 8. I take pi over 8. Double of that is pi over 4. Cosine of that is radical 2 over 2 times 2 is going to be 2 radical 2. So I'm going to have 2 radical 2. So that's my point. Next, you go to well, we get here pi third, divide that by 2. So we take each of these numbers, pi 6 now, double of that is pi third, cosine of that is 1/2 of 4 times that is going to be 2. Next, so we reached pi third. Next is pi over 2. Divide by 2. I will have pi over 4. Double of that is pi over 2. Cosine of pi over 2 is 0. 4 times that is 0. So we have reached the origin. Okay, we can continue like this to see where we go. It's instructive to continue. Now try to guess where we are going to go. We said that we are going to make kind of like a circle. This is going to turn around here, come down to this point, go, turn around, make to this point, and then go turn around here, make it to this point, and then come back. So it's going to take 8 of what we have done so far to finish. So let's just go and do one more point. So after pi over 2, I have 2 pi third. I divide that by 2, so I'll have pi third. When we double that, it becomes 2 pi third. Cosine of 2 pi third is going to be minus radical 3 over 2, and then well, I just noticed I made a mistake in what I just told you. So good that we did point plotting and figuring out by direct observation if what we said is correct. So uh, this petal is going to be traced to the origin, and then unlike what I just said a moment ago, it's not going to continue this way. Rather, it's going to turn around and complete the petal before it moves on. So okay, this is becoming embarrassing. This is a correction in incorrection. The first thing I said was correct, so let's see. Sorry for that. Pi third, so we are at the angle of pi third. Double of that is 2 pi third. 2 pi third is cosine is going to be minus radical 3 over 2. So times 4 is going to be minus 2 radical 3. So at pi third, we are going to be at this location. Now let's continue at the 3 pi over 4. So let's continue. So what I said at the beginning was actually correct, and then my correction was incorrect. 3 pi over 4. At 3 pi over 4, our double of that becomes 3 pi over 2. Our cosine becomes minus 2. Excuse me. Our cosine becomes minus 1, and then we multiply it by 4. So we are going to get minus 4. Okay, plan B. I realized making too many mistakes with the angles and their trig functions and such. So here is how to do it in a more robust way. So what we are going to do is to make our table just like we were doing on paper before. There doesn't seem to be a way to get around that. We go make our table. It's going to be a little bit lengthy because of this coefficient 2 here. The higher that coefficient is, the more work we have to do. So I erased whatever points we had here after this half petal was finished. To continue, what I recommend doing if you want to see the progress and you want to do the tracking of the curve by hand, here's how to do it. First, we go ahead, make a table. What is this table? Essentially, the table of trig functions that you have seen in your textbook multiple times. So here I have all the famous angles. So from 0 all the way to 2 pi, I list all of them, and then I list cosine of all of these angles all the way through. So we list the famous angles and their cosine all the way through. Then we notice that our problem is cosine of 2 theta. So I'm going to label these angles 2 theta, and these are then of course cosine of 2 thetas. So what is going to be theta itself? Theta is going to be half of whatever angle we had here. So if this is pi 6, this is going to be pi 12. If this is pi 4, this is pi 8. If this is 5 pi 6, that's going to be 5 pi over 12, and so on. So these angles are not readily available to us. They are not in our tables and such, but when we are using them, we are doubling them first, so they become the angle that we are familiar with, and then we have these values in our memory or calculator or something, and then we can use them. Finally, at the very last, we have to do a simple thing. You multiply this thing by some number, the radius of the rows. So that problem had 4 cosine of 2 theta. So I'm taking all these numbers and multiply them by 4. So in short, we are making a table of all the famous angles and their cosine. Now on the left, these angles are going to be half of these because that multiple is 2. these coefficients, these values are going to be 4 times that, because the radius of the rows is 4. So you need to make this table so that you'll be able to follow the rest of the discussion and the graphing. We are not going to have access to this page when we go to the other page. Unfortunately, we cannot have them side by side. We kind of need sort of a double monitor for this. So now I'm going to go ahead and continue on this page. So again, we have half of the first petal, and then we are going to continue after that. So we had reached the angle of pi over 4. Double of that was pi over 2. Cosine of that was 0, and that's why we reached the origin. And then the next angle is going to be pi over 3. And double of that is going to be 2 pi over 3, and cosine of that is going to be minus 1 over 2. Let me go ahead and enter these numbers here. So I have the angle is 2 pi third. So the angle was pi third. Double of that is 2 pi third. Cosine of 2 pi third is minus a half. Multiplying it by 4, I will have minus 2 here. So that's our next point. After that, we are going to go, so we're entering numbers from that table we had. Our theta is 3 pi over 8, and our the number 4 cosine of 2 theta is going to be minus 2 square root of 2, and that's going to be the next point. After that, our angle is again from that table 5 pi over 12. So I'll go back, make that table by hand, or make a print of it and then use that. And this is going to be minus 2 square root of 3. So we kind of see that we are progressing in the right way. The reason I noticed something is wrong is the curve just didn't look right. Next, our angle was pi over 2 from the table, and then our double of that will be pi. Cosine of that is minus 1 times 4 is going to be minus 4. So by the time theta is pi over 2, cosine of 2 theta is minus 1, so we are down here. Notice this kind of handle looking thing. That is a quarter of our curve. We continue again entering numbers from our table. 7 pi over 12, and for that the last column of entry was minus 2 radical excuse me. So we see that this is nicely curving back. Next one, so we double check, making sure we are not 5 pi 8. So the curve has to look like a rose, and that is going to be an indication for us if we are making a mistake, typing something incorrectly. This is the shape is helping us. So we are nicely progressing toward the pole again. Next one we have again entering from that table 2 pi third, and the radius was minus 2 in this case. Finally we come to the pole. We are at the angle of 3 pi over 4, and that double of that is 3 pi over 2. Cosine of that is 0, so our radius is 0. So what we have done is we have arrived at that point again. We have arrived at the pole again. We continue. So that's the nature of graphing. That's the nature of graphing. We have to get used to this because that level of detail is needed in calculus. So 5 pi over 6, 4 cosine of double of that becomes 2. So we arrive at the origin. We are continuing. So we are going to make this half petal here. And next angle is 7 pi over 8. And the answer here is 2 square root of 2 from that table. Again, we're checking that we are nicely going toward that point. Next was 11 pi divided by 12, and cosine, 4 cosine of double of that was 2 square root of 3. Finally, we come to angle pi. So we have made it all the way to pi. Double of that is 2 pi. Cosine of 2 pi is 1 times 4. I will be at 4. So we made it here. So we started at this location. We went gradually like this. We came around. We made this. We make the second loop. We came all the way to this tip. And I guess by now you get the idea. We can continue by making that table and come and plot it. So we are going to get the other half of this picture. That's going to go all the way to here, come back down and continue. Once you have enough of the points, you can also go to your second guess. So what is it? So we know it is this kind of a shape. So one petal of it obviously has to be here, then the other petal has to be here, and the third petal has to be here, and the fourth petal has to be here, and then we better be correct after all this work. You can always do a few of these points to make sure you're on the right track. Okay, thankfully that was done right. Now let's go back and have a second round of discussion about where are these tips and where are these approach angles, meaning like if I drawing these slices here, at what angles am I coming toward the origin? It's a simple case of solving some equations. So what do we do here? Let's take this problem again. So we had the problem of r is equal to r is equal to 4 cosine of 2 theta. So we had this picture. We got this picture. It came like this, came like this, came like that. Perhaps a little bit better looking than this. So that's our lucky sign. We want to know several things about it. First of all, where are these points? Well, it's kind of easy to tell in this case, but in general, if our numbers were different, where would we find these tips? Next, the question is, where are these angles? The angles at which we are approaching the origin. Okay, sorry for that. So let's first go ahead and find these tips. Well, that's when r is either 4 or minus 4. So what we need to solve is when the cosine of 2 theta, so either you go at 4, you go at minus 4, you reach your tip. So cosine of 2 theta has to be either plus 1 or minus 1. Let's go one at a time. Cosine of 2 theta being 1, at what angles does that happen? Well, the angle has to be 0 or 2 pi and so on. So the angle will be half of this at 0 or pi. When theta is 0 or pi, we reach the location 4. R becomes 4. Well, what about cosine of 2 theta becoming minus 1? Well, 2 theta has to be either the angle pi or either pi or 3 pi. So theta, we go find all the angles in the first circle. So pi over 2 at 3 pi over 2. So at these cases, r becomes minus 4. So what does that mean? When r is 0, I'm here. Excuse me, when theta is 0, I'm at this location. And then when I reach theta equal to pi over 2, so let's do it like this. I am at theta equal to 0 and the radius 4. And then I go until theta becomes pi over 2, but by my radius becomes minus 4. So my next location, let me write the individual variables so that we don't confuse it with polar coordinates, with Cartesian coordinates. So if angle is theta is 0, r is equal to 4. Then when theta is equal to pi over 2, r becomes minus 4. So while we are pointing this way, r is negative, and therefore we end up at this location. And then we come to the angle theta equal to pi. So theta is equal to pi. R becomes 4 again. Finally, when theta is at 3 pi over 2, so theta becomes 3 pi over 2 and r becomes minus 4 again. So by the time we have gone around the circle and came down to this point, the location on the curve is actually up here. Okay, so these are the tips, the 4 tips that we wanted to find. Here we found them. Next question is, at what angle do we approach the origin? So again, let's consider r was 4 cosine of 2 theta. Coming back, going to pole, that's what we are after here. At what angles do we come back to the origin? Well, cosine of 2 theta has to be 0. At what angles do we get 0? Well, at pi over 2 and well, 3 pi over 2, so on, 5 pi over 2, 7 pi over 2, odd multiples of pi over 2, that's where we hit. So theta itself is going to be at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. We typically stop at the range of angles between 0 and 2 pi, unless there are some other reasons to go after more. So these are the angles at which we are approaching the origin. So that is where these dividing lines are. This is pi over 4. This is coming here at pi over 4. Of course, this is at 3 pi over 4, 5 pi over 4, 7 pi over 4. So we said the trick in this case is to draw all the dividing lines and then fit the petals between those dividing lines. So you notice our discussion became much lengthier than before. Nature of graphing is just like that. Pictures that are not familiar to us They're not just ordinary pictures that we have seen before, like we have seen circles, parabolas and such, but we don't come across roses, unfortunately, every day. And so we have to spend the time, find a little bit of detail and put them all together. If something looks uh, kind of out of place, that probably indicates we have made a mistake in our arithmetic, and that's the problem I had here. I had a couple of points off where they were supposed to be because I got confused between a theta and 2 theta. Okay, until next time, so please do as many exercises as you can. Read your textbook. Go back and review other cases as well, so that you can respond to all of these cases all at the same time. The only thing we did with respect to the picture that was in the software is that we said you have to make 2 separate cases. One was for 5, 9, 13, and the other one was 3, 7, 11. The one has a tip at the top and the other one at the bottom. Okay, until next time, good luck and God bless.